In this video, we're going to provide some hints, and I'm going to try to provide some hints on how to go about designing the circuit required by lab number 6 in Engineering 250. The goal here is really to use the modularization that we've talked about, building on what we have already done, as well as finite state machine design that we've learned in the class, and use those to implement the circuits required here. Now, what we're going to do is basically use mostly the stuff we've learned, we have created in lab number 5, which was the 5-5 timer. And then we're also going to use the three-way intersection that were created in lab 3. So we're going to use those circuits pretty much unchanged because we're going to need those functionalities. And this way, we're going to do the small pieces in their own schematics and then combine them in the final schematic and put all the pieces together. So and the expectation is that you have read lab number 6, you understand what lab number 6 is requiring you to do, and this video is supposed to just kind of give you a little bit of help to get started on it. So let's go ahead and start. So in lab 5, you already had created a timer circuit where RA was 1 megaohm, RB was 1 megaohm, and C was 1 microfarad. And what would happen is your circuit, basically the output would be the clock, what we call a clock, and we can do a timing diagram of that shortly. And then the idea here is that we're going to take 2 flip-flop and we're going to create a delay circuit. So we're going to have an in that will come into this circuit, and this in will be fed in to 2 flip-flops. And we call first flip-flop D1, second flip-flop and the output Q1, second flip-flop D2, and the third and the output Q2, and we're gonna call this one output. Okay, so that's the in and the out, and then the clock, basically this circuit that you have earlier provides the clock. And the claim here is because this clock, if you remember, the period for this clock was roughly 2 seconds. Okay, and so what we're going to use, and so let's go ahead and finish this schematic. If this was a real schematic for the 2-second delay, the way I would put it is I would put it in a schematic to kind of demonstrate to the world how I'm putting it together. You may even come along, although you don't, for the module, you don't have to put it in there. But if I'm testing it, I would have an LED and a resistor to 0, so I know when the output goes output high, and I may create the in using a resistor and a connected here with a switch to a ground, and that would be my circuit. Now, I also have to tell the world about an ID block, which would say who's the designer, what is the project, some name for the project. This project would be a 2 to 4 second delay project, and then the designer's name, which would be whoever designed it, you or whatever, and then a date. Then this is referred to as an ID block. And then you also going to have another block here for the parts you're using. For example, that you are using, there are 2 parts. If you remember, you said like U1 and U2, and you already are familiar with U1, which is a 5-5 timer. The stuff that has a number, that's all you have to say for description. And so this would be, but the other one, I'm going to use a flip-flop, which is 74 LS74. And then whatever VCCs or ground connections I have, I'm going to put them in here. Now, I took the liberty before doing this of going to the data sheet for 7474 and pulling out the physical drawing of that, so I know what the pin numbers are, so I don't have to go we don't have to flip back and forth. So this is in the data sheet for the part 74 LS, or in your case, HC would be. And then one of the items in the data sheet is the drawing. So I'm going to just grab this. So in order for my schematic to be complete, I have to say which pins I'm using for D1, which one I'm using for D2. So I'm going to say this pin is 2, then the output Q1 comes out of pin 5, and then D2 is connected to 12, so 12 goes the D2, and the Q2 comes out of 9, if you see it over there. So a bunch of things, like for example, 8. So 8 is no connection. I could add it to my description of my stuff with the no connections, but for now I'm going to skip it. So I'm not using 8. I'm not using 6 for the purposes of this exercise. And then pin clock 1 and clock 2 are pin 3 and pin 11. Okay. So my schematic is pretty complete. The only thing I have to say, all the pins that I'm not using, for example, for this one, pin 14 is connected to VCC, and then all the clears and presets and all that will be connected. So 13 and 10 is to VCC because I don't want to clear it. I don't want to do that. So, and then on this side, pin 1 is got to go to clear, and then PR preset also has to be high. And then the only ground we have is pin 7. So I'm pretty much done. So that's the schematic. And notice when I do the flip-flops, I am not really trying to emulate the physical diagram at all. I'm logically representing. So when somebody's wiring this or somebody's trying to think about this, they don't have to worry about what the physical drawing is. They only have to worry about which pin is connected to what. And that's all they have to do. So I'm done. And what I have is a 2 to 4 second delay. Now let's find out how did we get 2 to 4 second delay here from this. So the best way to do that in this particular case, the best diagram is the timing diagram, because that's what allows us to see what is happening as the clock is running, and the delays, specifically the logical system diagrams and state diagram and things like that don't give us that information. So this is one case where timing diagram is very useful. So we've got the clock coming in, and because we use 1 megohm for the resistors and 1 microfarad for the resistors, we can pretty safely say that this clock is pulsing at the period of 2 seconds. So what does that mean? That means the distance from a rising edge to a rising edge, which is a period, is equal to 2 seconds. Okay. So if it's equal to 2 seconds, then what happens if, let's say, in changes? So if in is coming in, and if my in changes somewhere in the period, I don't know where, somewhere in the period goes from high to low or low to high, it really doesn't matter. The important thing is, when does out go from high to low or low to high in reaction to the input? What we know is these flip-flops, if you read the description, these flips are edge triggers. That basically means the only time they look at the input is during the rising edge of the clock. So it would be right at these places, okay? So what basically then what happens is that for the first flip-flop, the input is not seen until this clock comes along. So Q1 on pin 5 will not change until you arrive here, okay? Now, so that's great. But all I can say, the delay from this point to this point, all I can say about this delay is somewhere between 0 and 2 seconds, depending on where the edge changed. If the edge changed really close to the second rising edge, it's going to be 0, close to 0. If it's changed close to the first rising edge, this being the first rising edge, then it's going to be roughly 2. So I don't know. It's somewhere between 0 and 2. In order to guarantee I have 2 to 4 seconds, I have to wait another clock, which that's why the second flip-flop gives me that, because the second flip-flop does not see the input going low until the third clock cycle, until the third rising edge, which is right here. So Q2 will not change until roughly here. So that basically ensures that I have a minimum of 2 seconds, a maximum of 4 second delay. That's what's kind of what we were asking for. So once you're done providing this to whoever is reading your material, at this point, you can claim that you have a module, and this module is your delay module. And you can put an input in it and put an output in it. And basically, you're guaranteed that you get 2 to 4 second delay. You don't have to redraw this. Just putting this in there, you're done. So every time somebody needs a delay, you build a copy of this, and that's their delay. So we're going to need 3 copies of this delay for what we are about to do. Okay. Now, so this is the delay portion. We are done with the delay portion. We've got our delay module. Now we can move into the next portion of our design. The next portion of our design comes from lab 3. So if you remember, in lab 3, you build a circuit. You had a 3-way intersection where you had east, west, and south, for lack of it, cars coming in, but you only had red and green. So when you designed the part, when you designed the 3-way, you only gave permission. You didn't worry about whether you have to have yellow and they have to wait through the yellow or not yellow. If permission, they had the permission, they got a green. If they had no permission, they got a red. So this was more of a permission. So I'm going to rename it. You had the car presence, when you had you build this modules, and I'm going to draw it as a system diagram, shows the module. You're going to have a car east come in, you had car south come in, and you had car west come in. And you said 0 means no car, okay, and 1 means car is present, okay, for the input. For the output, you used to have this. And rather than me calling it green, like we call it green, this is only saying permission for the west to go. Not that they can go, but it has a permission to go because of the priorities, it has an opportunity to go, or a permission for the south to go, or permission for the east to go. Not green. Green is got to be qualified. Okay, So in right now, I'm going to take west as an example and do that, but you have to repeat what we are about to do for west, for south and east as well. Okay. So when can you let west go green? So in order to do that, you have to take this and you have to end it with the other 2 lane being red. So you have to make sure that the south is red is true. So it's already in a red position, because remember, it could be in yellow. Just because west has a permission, could be south had the permission to go, and it has to turn yellow, has to turn red. If you're not waiting for the red, you could have 2 cars having green, or 1 could be yellow, 1 could be green, you're going to have a problem. So you just got to make sure that the other 2 lane, which is south is red and east is red. And if both of these are true, then you can allow this to go. And that's how you create the east red, not east west, east red is true. Then if the west has a permission, then you can say, okay, west has the permission to go, so they got to agree. Okay, now the interesting things become, what if when the green goes away? What do I do when the green goes away? How do I know when the yellow is, and all that kind of stuff? So in order to do that, I'm going to basically extend this, and I'm going to say, okay, for the west, when do I give the yellow for the west? So what I'm going to do, we're going to take the west green, okay, and we're going to run it into this other part, which is our delay module. Remember, we built the delay module. Here's what we're going to use it. And we're going to end up with the delay west green, okay? The signal that comes out of that. That's 2. So what are the relationships? So our west green is high and then goes away. In the past, in the lab 3, we had the green, we had west light go immediately red, but we can't do that. We gotta have a yellow before we go that. So what we did, we ran it through a delay. So now we have a signal called delayed west green, which means this thing is actually gonna go away, and the distance from here to here is 2 to 4 seconds. That's how we did it in design the delay. So now how do I get the yellow going? So the yellow signal, I better use the same terminology. So the west, the light that is connected to the west yellow, what it's going to do is going to basically, we want it to come on as soon as green goes away, wait for 2 to 4 seconds and go away. Oh, that's easy. It looked like that happens when west green is 0 and the delayed is 1. So all I have to do is, this is going to be a west green knot ended with delayed west green. So now how do I do west red? Well, I want the west red to come on after the delay is gone away, which means I'm expecting both this to be 0 and this to be 0, which is okay. So west green will be west green, west red, I'm sorry, west red is going to be equal to west green knot and delayed west green knot. So now you got it all made. So once you got this lane done, you can start creating the same setup for the south and for the east, and you now have a set of three-way intersections where the green comes on. When the green goes away, yellow for that line comes on, and before anybody else can go green, you have to have the red come on, and then they can go green. This way you avoid any kind of accidents and all that kind of stuff. So let's go back. This is about the providing you hopefully enough information so you can go off and implement lab 6, which is a three-way intersection with red, yellow, and green. Okay, so now let's go ahead and take a look at what we've talked about as a quick, brief overview before we call it good. So we started this with a couple of things. One, showing you how to create a 2 to 4 second delay using a timing diagram to show you that is indeed 2 to 4 second delay. And also a little primer on how to do schematics, making sure you have the ID block, make sure you have the component block, make sure you have pins on all the parts. And again, once again, you don't draw the physical part, but rather you draw the logical version of that. So whatever, you can move the pins around to where it makes more easily understandable by someone who's reading it. And the stuff that is either high or low and has no logical impact, you can put it on that component table to make your circuit a little simpler for someone to look at, okay, and understand. And typically, if you have an output or an input, you want to put switches and LEDs there so people know how to test it and how you expect it to get set up. Once you're done, then you use basically a system diagram so that other people can literally, once you have designed one of these parts, if somebody wants 10 of these things, they can just keep copying your design and they've got 10 delay. In our case, we only need 3 of these delays. So you got to do 3 different 74 LS74. You only need one 5-5 timer because that clock can be shared across all of these devices. But you do need 3 74 to create the 3 delays. And then we came back here and said, okay, this is the stuff you had from lab 3, where you got the cars coming in and you were using them to give permission to go. That was used to permission. If they give them the permission, if the priority was high enough for the light for a car to go, you would give them a green. You didn't have to worry about having to wait for everybody to turn red, because as soon as you took the permission away, they were red. In this case, we have the whole yellow to put up with, and using our delay and using what is shown here, you can create the signals you need. Now, this process is using modularization, is using what you built before. That's not to say you can't take the finite state machine design process, which we have talked about in chapter 5 of Engineering 250, and do a state diagram of what you need to do, what are the different 9 states that you have to deal with, do the present state, next state table, write the excitation input, and draw the circuits. The only thing is, modularization is really important. You'll find out that doing it from bottoms up, like as design is done for the whole system, it's just too much. It's harder to do than building each of the small blocks and then connecting them together, as we have talked about in the past. This is concept of modularization, which is throughout everything we do. Hope that helps. And if you have questions, you always know where to ask. Take care.